Hey, hey, ready for part two? I'm not. Let me get to where I left off. Okie dokie. Here we are. Okay, let's see. All right, for the second 25, here we go. Here is this rotate clockwise. Notice it's not counterclockwise. So we start by looking at our original points, which are here. It says rotate it 90 degrees clockwise around the origin, then a reflection across the x-axis. Okay, so clockwise is the same thing as 270 counterclockwise. So that is switch and change the second, followed by a reflection across the y-axis. Across the y, change the x. So if you look closely, I took the originals. Oops. -2, 1. We're going to switch and negate the second. So it becomes 2, 1. -2, 1 becomes 1, 2. Let me see if I can show you an example. Here we go. -2, 1. We switch 1, -2, and switch the second. So that becomes 1, 2. And then across the x we change, across the y we change the x. So my point should be -1, 2. And you do that for all three coordinates. And you should get what looks like this. Again, switch and negate the second. 3, 0. And you really can't negate the 0. And then across the y, change the x, -3. Voila, you have -3, 0. And then you would have -3 down here. Okay, so be careful, be careful, be careful, be careful on the semester exam. Read carefully. 90 clockwise is the same thing as 270 counterclockwise. All right. Translate the trapezoid by adding 4, which means you're going to the right, and subtracting 2, which means you go down. Just move the points. And over on the left-hand side, I did each one for you. Okay, add 4, and then the rule is y equals x. You just switch. So over here, I've added the 4, subtracted the 2, and then I just switch the direction. I'll do one with you. -5, 2. Add the 4, subtract the 2. -5 plus 4 is -1. 2 minus 2 is 0. And then we're going to just switch them to 0, -1. All you do is move the points. Know the rules, move the points. Just move the points. Don't worry about what it's going to look like. Don't try to visualize it. Move the points. They're 100% accurate. The next one, rotate the quadrilateral 180 degrees. Remember the rule. 180 is negate x, negate y, followed by a dilation of a scale factor of 3/2. Remember, dilation scale factor is just a multiple. Multiply. And don't worry about multiplying by a fraction. Numerator times numerator, denominator times denominator. Let's take this one over here and blow it up. -4 over 1 times 3 over 2. How many times can 2 go into 4? -2 times. 2 times 3 is -6. Or -4 times 3 over 1 times 2. -12 divided by 2 equals -6. Okay? It's just a multiple scale factor. Each point, 1 point at a time. Rectangle ABCD is reflected over the y equals 1 axis. Remember, y equals 1 looks like the x-axis. It's horizontal. It's through here. Then translated by a rule to map A prime, B prime, C prime, D prime. First, we're going to go over, and then we're going to slide over and up, and we end up going over 7 and up 4. These are going to be the tricky ones. Y equals -1 or y equals or x equals. X equals -3 looks like the y-axis. If they have 2 on this review, you guarantee you're going to have one of them on your semester exam. Y equals -3 is vertical and looks. We're going from here to over here. Remember, you are symmetric, same distance, equidistance to the line of reflection. So however many units those are apart, same amount of units. These are going to be apart from the axis. Then how do we go from here to here? It's a translation. We went to the 3 right and down 6. What are the coordinates of Z? All you need is Z. Rotated 90 degrees counterclockwise. Switch and negate the first about the origin. Then translated, subtract 5 minus 2. One step at a time. First step, second step. All they want is Z. Don't worry about any other letter but Z. What are the coordinates of D? Again, one letter. Concentrate on one letter. A reflection over the X, cross the X, change the Y, then multiply by a scale factor, multiply by 2, and we end up with -6, -4. Not hard, only want one letter at a time. One letter, one coordinate. Don't make it any harder than that. Okay, this is like the 6th or 7th problem. You have to know those transformation rules. Okay, here's another example. You have to read this one very carefully, especially on select all the statements that explain why the trapezoids are similar. Recall, congruent shapes can be similar, but not all similar shapes are congruent. This is the 2nd or 3rd time they've talked about this. It's going to be on the exam. Okay, first, look at the original. ABCD is bigger than the little one, big to small. Trapezoid ABCD could be mapped onto PQRS by a clockwise rotation of 90 degrees, with the center at the origin followed by a dilation with a scale factor of 1/2. Okay, we're talking clockwise. which is this direction. And that's exactly what it does. It's going clockwise. Take one point and move it. Start with, say, C, and move 1 point. C is located at -2, 2. Our rotation of clockwise, there's that clockwise. So clockwise is the same as 270 counterclockwise. Switch, negate the second. So switch, negate the second, which will make this positive, followed by a scale factor of 1/2. Scale factor of 1/2. Half of 2 is 1. Half of 2 is 1. Notice we end up at what do we end up at? 1, 1. Then it says 4 units to the left, followed by 4 units down. We should be at -3, -3. And if you look, we end up at -3, -3. So this one's tricky. You have to do 3 transformations. First, a rotation, followed by a dilation, which is getting it smaller, then followed by a translation, which is moving it, and we're concentrating on one point leading to the other, and that's exactly where we need to be. And I circled the wrong point. I circled the coordinate that I was looking for was 3, 3, and I circled the wrong one. So let me go back and erase that so it doesn't look so messy. And I apologize for that. This should be rotating over to here, and that's the point. 3, -3. These are not impossible, but you have to move 1 point at a time. You have to do more than one. Can be mapped onto by a dilation of a scale factor of 1/2, centered. If you move one of these coordinates, it's not going to work. The scale factor is off. We could have translated to the right and 4 units up, which is the reverse, multiplied by a scale factor of 2, 270 clockwise. So this one's a total reverse of the one we already did, because we're moving completely the opposite direction. So this one works. Trapezoid PQRS can be mapped onto EFG by a dilation of a scale factor of 2, with a center at the origin, followed by a translation. Move 1 coordinate and see if it works. Trapezoid, I'm working on this one. I'm going to show you 1 coordinate at a time. PQRS can be mapped onto EFG. So let's look at P. P is at -2, 2. With a scale of a dilation of 2, so times 2 gives me -4, 4, followed by a translation of 8 units to the right, 8 units to the right, followed by 8 units up, should give me a coordinate of 4, 12. And P, coordinates with A. So if we look at A is located at 4, 'I have to redo that one, make sure the answer key is correct. Dilation with scale factor of 2 with the center at the origin, followed by a translation 8 units to the right, and 8 units should be at 412. That one doesn't work. Let me come back to that one. Same thing here. Dog and bat are shown in the coordinate plane. Select all the statements that explain why. Take one coordinate A and move it for each and every one. Notice that D has to map on top of B. It can't be rotated by a 180 because the coordinates don't work. Dog can be mapped onto B. Dog can be mapped onto bat. I think I'm going to do a video with just these two on there because there's a lot of work. So I'm going to come back and do these last two problems on a separate video. If you look at each one, D maps onto B. A rotation of negative x, negative y by a scale factor of 1/2. And if I do each one, you're going to see that it does not match. -3, 6 does not map onto 1, -2. The only ones that do are these two. This one here and this one here. Those two work. Looking at this one, ABC is a dilation of DEF, where this is your old one, this is your new one. And then you notice I've marked the pictures. One's big, one's small. The big was the original. So in order to get the big one to the small one, you would not go with a scale factor that makes it bigger. You need a scale factor that's less than 1. ABC is a dilation of DEF, which would be a scale factor that is less than 1, 2/3. That would work. The perimeter of the big one should have a scale factor that is bigger than the perimeter of the small one, which is 2. Big over small, 3/2. That makes sense. That is correct. On this one, the order is wrong. They have small side over big side over small side. Look at each one of those pieces and make sure that they're putting them in order. Angles are preserved because they are similar. Okay, be careful. They want to know whether it's a theorem or a postulate that corresponds with congruence or similarity. These sides are not congruent, but they are similar. And we have a side, an angle, and a side. The rest of these are congruence, so it'd be side, side, side congruence. And this is angle, angle, side, which is only available for congruence. Know this question. This is an easy one. And we've done plenty of practice. We should be able to nail those. Notice they're marking congruence with similarity. You want to make sure that you understand proportionality versus congruence. Proportionality, not congruent. That's why they're similar. 37. Select all the statements that are true by cpctc. Corresponding parts of congruent triangles are congruent. RT coordinates to R prime T prime. That would be cpctc. Notice the next one is SR compared to ST. They're not corresponding, so this one doesn't work. Triangle RST corresponds to R prime S prime T prime. Corresponding, correct. Angle T coordinates to R, no. Angle R coordinates to R prime, yes. I'm going to look at the answer key for this one. Now that I am thinking about it, those triangles are congruent, not by CPCTS. I'm going to have to double check whether the answer key or not says that is true. I'll get back to you on that one in just a little bit. I know they're congruent because they're corresponding, but they're not congruent by CPCTC. They're congruent by side, 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 side angle, side. I'm going to come back to this one. This one I believe we did in class. We have a side that's congruent. We have a bisector of this angle. So that gives me these two angles up top. And by the reflexive property, so we have side, angle, side. Because the two triangles are congruent, then we can say CPCTC. Okay. Again, we have segment bisectors. So we have two segments that are bisected. That's one. Then we have two. And the angle is vertical and it's in the center. So that's side, angle, side. And we have to make sure that the last line of the proof is always exactly what they want us to prove. Watch the placement of the letters. This is side with the angle and then the side. This is angle, angle, and we don't get the side till we turn the quarter. Draw the triangles. It'll take you 10 seconds to draw them on the semester exam. If you don't draw them and you don't mark them, you're going to miss them. And here's that infamous flow proof. Given leads to congruence, leads to the end of the proof. Given is a simple angle. And then we have another angle. And then CPCTC is the last thing that follows. Okay, here's that side splitter theorem. If the lines are parallel, then the pieces are proportional. Make sure you set them up correctly. Big over small equals big over small. Cross multiply and solve. You're going to see decimals, you're going to see fractions. That's okay. 42 is tricky. When we set the three triangles up like I've taught you, big, medium, small, you're going to find that they don't give you corresponding pieces. You're going to find that they're asking for x, which does not correspond to 48 that they give you. You have 52 corresponds to 48, but you don't have this 20 that corresponds to x. How did I find that? I had to use Pythagorean's theorem. In order to get the pieces that correspond, I had to use Pythagorean's theorem. And actually, I found the 52. They give you the 20. I had to find the 52. The 48 was a distractor. It doesn't work at first. We have to be very careful. In the picture, they give you the 48. They're asking for x. And they give you a 48 here. And they give you a 48 here. But those do not correspond to everything else that they give you. Let me say that again. They give you the 48. They give you the x. And according to this picture, I can't see it. There it is. They give you the 20. But when I put the 20 on, it corresponds to the x, but the two 48s do not correspond. In order to get a pair that correspond, we have to be smart enough to go back and find the 52. That tells me they're going to give you a tricky one. The pieces have to correspond. If they don't correspond, look for Pythagorean's theorem to find the missing side that does correspond. All right, on number 43, be careful again, because these are perpendicular, then they're broken up proportionally. Perpendicular have to be parallel, so they're breaking it up. It's another side splitter problem. Make sure that you're putting parts that correspond. 8 plus 11 is going to correspond to the 8, and then x plus 9 is going to correspond to the 7. Set them up, cross multiply, and solve. Remember, order doesn't matter as much as consistency. This one looks terrible, but it's really not bad. Look at 42 carefully. Make sure you do this one on your own. And you'll see what I'm talking about the pieces not corresponding and why it's so important that we have to go back with Pythagorean's theorem and find 52 using the numbers that they gave me, 20 and 48. Remember the one we did in class that was on the FSQ that I gave you? We had to use Pythagorean theorems twice, so they're going to give you a problem.